everyone. Alright, it's time. The fundamental theorem of calculus, although it probably should be called the fundamental theorem of analysis. Alright, so recall from our calculus days that if you wanted to compute the integral of a function, all you needed to do was find its antiderivative, a function whose derivative is f, plug in the endpoints, take the difference, and that's it. All you had to do. None of the Riemann sum junk, no Archimedean partitions, just find this and do that. Guess what? We're going to prove it. And in fact, it's probably pretty close to a proof that you may have seen in your Calc 1 course. Okay. So, note, the statement of the fundamental theorem here is exactly the same, with very little difference from what you saw in Calc 1, other than some inclusion of, being a little bit more mindful of domains and things like that. But, right, so a non-degenerate interval from A to B, we have a capital F that is continuous, differentiable, note, not necessarily at the endpoints. Ooh. And I've got a Riemann integrable function so that the derivative of capital F is equal to f of x for all x from A to B. Then, the Riemann integral can be computed by simply doing this. Alright. So, virtually, note for other things from calculus that we've had to sort of, make rigorous, there was a lot more, build-up of, oh, we gotta talk, about closed subsets of the real line, or, what is an interval, really? And things like that. But here we see the fundamental theorem is it's still a fundamental theorem. And that's it. But, maybe you notice that this is the first form of it, and so that means that we're probably we're gonna make it less fun. But anyway, let's prove it. The good old fundamental theorem of calculus. So, pick a partition. Okay, now, so for each subinterval, by hypothesis, our capital F is continuous and differentiable on the interior, so from A to B, excluding A and B. So that means that for every one of these, I can find a point that lives between the two, strictly, so that the instantaneous rate of change lines up with the average rate of change, and note, oh hey, that's equal to that. Alright, so note, this down here is delta x sub k, so multiply it over, we get that. Okay, now, hey, we've got a beautiful Riemann sum right here, and as we've already discussed, the Riemann sums hang out in between the infimum and the supremum. They hang out between the lower Darboux sum and the upper Darboux sum. Now, this particular Riemann sum is rigged so that this is what we get here, and you may, hopefully, immediately recognize this as a telescoping sum. So, this simply becomes that, and oh look, f of b minus f of a. Telescoping comes to help us once again. So, note, the lower Darboux sum of f for the partition P, and the upper Darboux sum for the partition P, always contains the quantity fb minus fa in between them. And since this is arbitrary, that means that the lower Darboux integral cannot exceed this value, and the upper Darboux integral cannot be less than it. So this is squished right in between the integral from a to b of f of x on both sides, and there we go. We have proven the fundamental theorem of calculus. And note, in reality, all we did was just, hey, by the way, mean value theorem. So here we see that if you want to compute the integral, you just need to find an antiderivative. Wonderful. That's it. So, this then kind of begs the question of, alright, well, when can you find an antiderivative? So that leads us to the second form of the fundamental theorem of calculus, which then sort of addresses the question of, alright, well, if you can find an antiderivative, great, you can compute a Riemann integral, but are there reasonable conditions that would guarantee that an antiderivative would have to actually exist? Right. And that is the goal of the second form, to sort of do the reverse. If you have an antiderivative, the Riemann integral can be computed. How can we find antiderivatives? Alright, well, it particularly involves the notion of an integral defined function. So, depending on where your math life is taking you, you've definitely seen these. You saw these in Calc 1, maybe for like a day or so. But if you've done some probability, or maybe some upper-level statistics stuff, you've ran across probability distribution functions, and yeah, you might be a little more familiar with these. Okay, so in order to properly state it, and prove it, and use it, we need to introduce some conventions regarding the Riemann integral. Okay, so first things first, recall that a partition is any finite subset that contains the endpoints. I left that part out. And there it is. Okay. So that would mean that if we applied that definition of finite subset containing the endpoints, well, the degenerate interval that consists of just a single element here, well, then the only partition of it would just be itself, the single point A, so all of these would just equal A, which would mean all of the lengths of my subintervals are 0, so my lower and upper Darboux sums would always equal 0. So in light of this, for any function defined on the singleton set A, we'll just say its Riemann integral is equal to 0. Right? Note, any function defined on such a set is automatically bounded, so that's good. Right, and so we'll just define this to equal 0, right? And if you think about sort of the visual of this, this is a single line at the point A with a height of f of A, and note a width of 0, so it's a rectangle, but with no area, because it has no width. So, pretty reasonable thing to define. Okay. So that one shouldn't be too controversial, but the next one is maybe the weird one to think of. Now, if I give you a partition of an interval, I can reverse the partition by defining y sub k to be x sub n minus k, right, where k will run from 0 to n. Note that y of 0, plug in 0 here, is x sub n, which is b. And then if I plug in 1, I'll get x sub n minus 1, which is less than b. And so on and so forth until I get all the way down to y sub n, which would be x of 0, which is a. So this partition, I can reverse it as follows. And now, if I were to take this and treat this as if it was a genuine partition, right? So if I were to look at its delta, well, its delta will be negative the appropriate analog of the x sub k. In this case, it would be n plus 1 minus k. Okay, so here I'm just applying the typical logic to the partition, assuming this was a partition, but it's in reverse. And note the formula that's it spit out was this. Likewise, for any bounded f, I can then look at m sub k, the infimum of f on these intervals here. And now note, because the y sub k's are descending rather than ascending, I need to have this swapped. But right, I can still talk about the infimum on this set. But note, this interval right here would be the corresponding interval here, which means this n sub k would just be the infimum of f on the n plus 1 minus k subinterval of the partition P. Alright. Okay, so note here I am replacing it with that, and I'm pulling out the minus sign. But note here, if I plug in 1, I have n. If I plug in 2, I have n minus 1. If I go all the way up to n, I then pick up 1. Likewise. So, if I reverse the order of the summation now, which I can, right, it's commutative, I'm allowed to swap it however I like. I then find, oh hey, it's negative the lower Darboux sum. So treating this as if it was a genuine partition and creating the thing that we would normally create just gives me the negative of the lower Darboux sum. And likewise, the same thing happens. We can create this, and this looks a lot like a Darboux sum, but it's actually the negative of the upper Darboux sum. So, for any Riemann integrable function from a to b, we define the integral from b to a to just be negative the original integral. Right, and note that sort of makes sense, because if you were to reverse the interval itself, well, the infimums and the supremums would not change, because, right, we're not screwing around with the function, but the deltas would go negative. Right now I'm recording, okay? We'll ask Mom, okay? Alright, bye. Guest appearance by Charlie today. Alright, I almost got through every video without her showing up and asking for food, but... Anyway, alright, so there we go. So, right, so this makes a bit of sense, because, right, if all we're doing is reversing the, how the interval is going, instead of going from A to B, it goes from B to A, then the only thing that would actually change in the Riemann sums would be, right, the width, right, the width would go negative. Alright, so that makes sense. So, note something now. For any integrable function from a to b, pick any x and y. I can always form this now. So I now have a convention that allows me to talk about the Riemann integral from x to y, where x and y are arbitrary elements out of the subinterval ab. Right. Now, at first glance, this may feel a little, yeah, okay, sure, and you're going to be surprised how useful this actually ends up being in conjunction with the second form of the fundamental theorem of calculus. So, like I said, the first form of the fundamental theorem of calculus tells us how to compute the Riemann integral using an antiderivative. The second form is addressing the question of how do we even know antiderivatives would exist, and as we are going to see, you need to do integral defined functions like this, and you need the flexibility of the lower and upper bounds on the integral to kind of be whatever they want. So we need to talk about the case when they're equal, or when the one on the bottom is bigger than the one on the top. Which you may have encountered in your calculus life, or probably maybe a U substitution caused that to happen. Right, and now, right, it just happens sometimes. Okay. Alright, now, before we get to the second form of the fundamental theorem of calculus, let us use this new fact to prove that integrals can still be split in twain, but the splitting in twain, and that is supposed to be a y right there. Not sure why that turned into an x, but it did. Alright. Alright. Integrals can be split in twain, but here note the twain splitting involves an x and a y, and there is no relationship between x and y. They could be any two elements. So your book actually has as a homework problem. Note here, I'm still using a as the lower. The book points out that you can actually have a third element, so you could put like a w here and a w there, and it'd be true. But we're not going to need that full generality, and also this is already going to be a proof that has 5 cases. If you make this a w, that like it basically boils down into I think it ends up being 7 cases. It's 2 more than we're already doing, but I was like, 5's enough, and this is all we actually need. But it is worth noting you can make this a bit more general. You can make a be whatever you want as well, but whatever. I'm not going that far. Let's not go nuts. Alright, so, and as we will see, this ends up being an incredibly powerful tool for creating integral defined functions. Good stuff. Particularly, this lets us get away with making integral defined functions on any non-degenerate interval. And if that sounds like something you take a derivative on, hey, maybe you're right. Alright, so like I said, there are 5 cases to break down, and the 5 cases are basically, alright, well, y is bigger than a, but what's y's relationship with x? So, that's what we're doing. So like I said, if this was also arbitrary, then you'd have to be like, well, what's this relationship with x? What's this relationship here, and what's that? And just so many cases. This is a lot easier to do. So note that if y is actually equal to a, if I do the integral from a to x, alright, well, I can add 0, and the integral from a to a is defined to be 0, and replace the top a with y because they are equal, and we can do that. Alright, super easy. Okay, so now let's say a is less than y, but y has not exceeded x. Okay. Alright, well, then, hey, this integral just splits in twain as it normally does. We've already proven this to be true. Yay, nothing weird happened there. Alright, next case to consider. Suppose that y actually coincides with x. Alright, so note we have taken care of, alright, what if y is a? Alright, now what if y is bigger than a? So note, y is always less than or equal to a is always less than or equal to y. So now we've taken care of the equal case, so we can always be assuming this. But what happens if y actually runs into x? Alright, well, the integral from a to x, then, is the integral from a to x. We can add 0, a integral from y to y. We can replace the top y with x, and replace this x with y. They are equal. There we go. Desired result. Alright, next up, x is strictly less than y, but x and a actually coincided with each other. Now, note this is different than just y being strictly less than a. We have x coinciding with it. Alright, now this one, note a is equal to x, which means that this integral would equal 0. And now here's where we're going to use the... So far all of the tricks we've pulled are when the integrals are have the upper and lower bounds equal. Now we're going to see, aha, good thing I have negative and I can swap, and then I can replace a's with x's because they are equal. Super cool. Alright, so that is taking care of 4 cases, and there's one more to do, and the last one to hit is what happens if a is strictly less than x, which is strictly less than y. That takes care of everything, right, because, right, we took care of the case of if y is actually equal to a, so now assuming y is always strictly bigger than a, and then now the question of, alright, where is x in relation to those two things? There we go. We've taken care of x bigger than y, x equaling y, x less than y when x is equal to a, and now finally a strictly less than x, strictly less than y. That takes care of all of them. Alright, well, that means this integral is allowed to be split in twain. Alright, so subtract this thing over. Alright, and well, we can swap the order of the integration by the negation, and hey, when you know it, we now have exactly the desired result, and we're done. Beautiful. Right. So note, x to y is proper, but right when it gets subtracted over, we are allowed to swap the order. Cool. Alright, beautiful. So with that, now under our tool belt, we can state the second form of the fundamental theorem of calculus, and then we will apply this and the previous proposition to give us kind of the full force fundamental theorem of calculus, and then equipped with that we'll prove every continuous function has an antiderivative. Cool. Alright. So, take a and b, so that a is strictly less than b, so we've got a non-degenerate interval. Take any Riemann integrable function, and define the function capital F as follows. Integrate from a to x. So note, an integral defined function, right? F is Riemann integrable, so all of these integrals exist. We chose a, so we have a lower bound here. Note that if x is actually equal to a, this spits out 0, so we needed that to have this properly defined. In a moment, we will allow the base point here to be arbitrary, allowing us to create an integral defined function and start it wherever we want. Okay, but now note, this function that we've created here, defined via an integral, will always be Lipschitz. So note, this is guaranteed continuous, but not only is it guaranteed continuous, it's guaranteed Lipschitz, so it's a little bit stronger. That's amazing. Alright, and then we will prove that if I know my Riemann integrable function here is continuous at a point, then this function must actually be differentiable at that point, and the derivative is what you think it should be. Okay. So, in some sense, this reveals that differentiation and integration are inverse operations of each other, right? If you want to compute a Riemann integral, find an antiderivative, and then taking the derivative of the integral, right, undoes it. So there is a sort of derivatives can be used to remove integration from the inside and from the outside. So, right, cool. All right, so We got two things to prove. Let's prove them. Alright, so the good news is that Lipschitz is pretty easy to establish since f is bounded, there is an L, so that we're always less than or equal to it. Alright, now pick x and y that live in AB. There are two possibilities to consider. So if x and y are actually equal to each other, then the absolute value of the difference of these two, well, x and y are equal, so that's equal to 0, and that's equal to 0, so nothing to do there. Alright, now let's suppose that x is strictly less than y. Alright, well, then we know, hey, I can split as follows. And that means that if I look at f of x minus f of y, alright, well, I can change the order within here. F of y must equal this, and f of x must equal that. Alright, and note the proper splitting in twain here. This difference is equal to that, so subtract this over. Alright, now x is strictly less than y, so we know that we can apply the following fact. And since f of t is always less than or equal to L, then we get this. And we're very happy. Okay. And when y is strictly less than x, we can handle it similarly. So, note, I use the x is strictly less than y part right here. If you wanted to, you could technically also prove that this fact is true for integrating from x and y just wherever, but we didn't, so we're doing it this way. Alright. Anyway. Okay, beautiful. So, there we go. We have proven that this function, capital F of x, integral defined, is indeed Lipschitz. Alright, now let's prove that if I know the integrating function, the integrand, that's the name for it, the function inside the integral, let's say if I know that's continuous, then I actually know that my capital F is differentiable. Alright, so given an epsilon, that means we can find a delta so that f of x minus f of c is strictly less than epsilon over 2, and that's good for all x that are within delta of c. Right, just unraveling the definition of continuity, throwing in an epsilon over 2 for good measure. Alright, so two cases to consider. So if x is hanging out between a and b, and x is to the left of c, but to the right of c minus delta, then for any y that lives in the interval xc, so note where that is, there are two things that can happen. Okay, so note, if y is actually equal to c, then, right, f of c minus epsilon over 2 is strictly less than f of c, which is equal to f of y, which is equal to f of c, which is strictly less than f of c plus epsilon over 2. Now, if y is not equal to c, then we have that the following holds. So note, since y now is strictly less than c, right, note where y lives, that means that y is within delta of c, so that should be a f of y right there, not an f of x. So that would mean that f of y minus f of c is strictly less than epsilon over 2, and that would mean this is bounded above epsilon over 2 and bounded below by negative epsilon over 2, and then you just add f of c across the board, and that gives us this inequality. So regardless of where y is, we know that this must hold, and now we know this is true, that's good for all y in this non-degenerate interval, which means we can apply some facts that we know, that this integral must be bounded above by the upper bound times the length of the interval, and bounded below by the lower bound times the length of the interval, right? So if you let your mind flow back to the first set of slides here, we get that. And now note, divide this over, which we can do because it is strictly positive. Subtract this across. There we go. We get that this in absolute value is less than epsilon over 2. Now, note, now this top part we're going to turn into some f of x's. Alright, so specifically, f of c, note by definition is this. X is strictly between a and c, so I can split it in twain like this. Note that this is f of x, and the x's and the c's changed there for no reason. That is straight up typos. Jeez Louise. Okay. All right. So the swap. That was just. This is just bad. Bad copy pasta right there. Okay. Alright, so then we can subtract the f of x over, and we get this. And now, note that f of x minus f of c over x minus c. Well, I could pull a minus sign out of the bottom here and bring it to the top. We can swap it like that, and note this is equal to that. So that tells me f of x minus f of c divided by x minus c. Oh, hey, that's a difference quotient, isn't it? Yes, it is. When I minus f from f of c, that's strictly less than epsilon over 2, which is strictly less than epsilon. Okay. Now you might be wondering why an epsilon over 2. Well, note right here I have a less than... Oh yeah, that needs to be a less than or equal to. Less than or equal to. Right. Yes. Right, so even though I know this is strict, that's not guaranteeing anything over here would be strict. So, yeah, that is the reasoning for the epsilon over 2. Let me fix that right there as well. Okay, beautiful. All right, so we proved now that if C is to the left of C, but to the right of C minus delta, then this inequality must hold. And you can do the same argument where x is to the right of C, but to the left of C plus delta. So then that means that for any x that is within delta of C and not equal to C, which note is either this case or the other one we just talked about, depending if x is strictly bigger than C or strictly less than it, note it can't equal it, this must hold. So given an epsilon, the difference quotient gets within epsilon of f of C for all x in AB that are within delta of C and not equal to it. So in other words, f is differentiable and its derivative is f of C. Wasn't that fun? That is a fun proof. I like that one. That was a good time. Alright, so we've now proven that if I have a Riemann integrable function that is continuous at a point, then creating the function based off of its integral will be differentiable at that point, and its derivative is the function itself. So we, of course, want to push that as far as we can, but in order to properly use that, we need to do the following. So here we will now combine the previous proposition along with the second form of the fundamental theorem of calculus. So let's say I have a and b, so that a is strictly less than b. I have an integrable function. It's continuous at some point. I pick some other point, and then I define my integral defined function where instead of starting at a, I just start wherever the hell I want to start. Now note, I have a formal definition for this. I am able to do this integration. I claim that the fundamental theorem of calculus, as we just proved it, is still true. Right, so it didn't matter if I started the integral at a, I could just start the integral wherever I damn well please. Okay, and the function's derivative at the point where the inside function is continuous will still be, f of d. G. Oh my god. Jeez, man. Some of man, these ones are a littered more littered with typos. Oof. Well, I was making all of these during, so my daughter's birthday was on June 23rd, so we've been having parties. My best friend came in for a visit. So very busy the past couple of days, as I'm sure all of you are having all sorts of fun during this wonderful summer. All right, cool. Okay. Anyway, so these are a little bit more hastily put together than the other notes, I guess, is what I was saying there. All right, so let's prove those results. Now, it's worth noting that this is essentially just the two previous propositions put together. So specifically, let's define G to be the thing we just saw in the second form of the fundamental theorem of calculus. And now let's let C be the following. And now note, this is a constant. This is just do this integral. C is some point that we picked. Just do this integral. This exists. Maybe it's 0. It's possible. A is equal to C. But if it's not, it's just some value. Now, something we proved is that this integral can always be split in twain, right? And it does not matter what the relationship of C and x are to each other. But now note, this is the constant C, and this is our original function f of x, and this is good for all x. So f of x is equal to g of x minus a constant. By the fundamental theorem of calculus, we know g is differentiable at d, with its derivative being f of d. And that would mean now that f must also be differentiable at d, because we know the derivative of any constant function is 0. And there we go. Beautiful. Good stuff. Cool, cool, cool. Alright, so we have now demonstrated via the fundamental theorem of calculus that we can create integral defined functions, and those integral defined functions give us derivatives. So here we see differentiation undoes integration. And similarly, undoing differentiation via integration, kind of what we do with the other form of the fundamental theorem of calculus. Alright, so the last thing to set up before we get to sort of the last big theorem here is the following. So, integral defined function. So an integral needs a closed bounded interval to be defined, but it turns out, well, you can always make it on any non-degenerate interval as long as you got some stuff to work with. So specifically, if I give you a non-degenerate interval and two elements and I need a continuous function, three cases now can be considered. So first, if a is strictly less than b, well, since f is continuous, that means if I restrict f to a to b, it's Riemann integrable, since every continuous function is Riemann integrable, and thus we can form this integral. If a is equal to b, then yeah, we can form the integral, which is equal to 0. And if b is strictly less than a, well, then f from b to a is continuous, and thus it's Riemann integrable. And note, we can still define the integral from a to b, even though b is less than a in this case, by just going, oh, it's the negative, right? As we've already established, that is a perfectly legitimate thing to do. So regardless, if I have a non-degenerate interval and elements a and b, and now note, I need the non-degenerate interval part to ensure that a and b are contained inside of the domain, so interval needs to be here. And, well, and as we noted, when it comes to theorems involving continuity and differentiability, you really want a non-degenerate interval. Alright, cool. So, regardless, this is always formable for any continuous function, and 2 points. So, we now hit the last theorem, which is that, given a non-degenerate interval, a function that's nice and continuous, and fix any point in the non-degenerate interval, then this integral defined function, which note, we know that we're able to form this by the previous discussion we just had, this function is not only differentiable, its derivative is not only equal to f, its output at a is not only equal to 0, it is the only function in existence with those properties. So there you go. Every continuous function has a antiderivative, a function whose derivative is equal to it, and it can be made unique, right, note, given some initial information, essentially. So, beautiful. There we go. That's the theorem. Let's prove it. And as kind of noted, we've effectively done all the heavy lifting. There are just a couple of minor points, just a couple of provisos that we need to consider. Alright, so the first one is, alright, it's pretty easy to see f of a is equal to 0. So, check that. Next up, why is f differentiable and why is its derivative lowercase f? Well, pick an x that lives in the interval. To actually apply the previous proposition, we need to know that a and x live in some closed-bounded interval for an alpha and a beta. Alright, that are strictly less than each other, right? Note those was part of the hypothesis, so we just need that, and this is pretty easy to demonstrate because, well, if x is less than a, then you let alpha be x and beta be a, and if a is less than x, then alpha is a and beta is x. Okay, so the only case that's interesting and worth discussing is what happens when x is actually equal to a. Well, then, since the interval is not degenerate, good thing we assume that, I can find a y that's not equal to x, and thus it's not equal to a or x. And then now we have either x is less than y or y is less than x, so we do exactly what we just did before, where alpha and beta are chosen so that we have a strict inequality between alpha and beta, and the elements x and a live in the interval, and note that I only need to care that x lives there. Alright, beautiful. Alright, so we know that we send a to 0, and we now know that we are differentiable, and our derivatives line up with what we want them to. Alright, so Let's get that uniqueness, shall we? Alright. So, suppose that I have a differentiable function whose derivative is f, and it sends a to 0. Alright, well, let's let h equal f minus g. Alright, well, by definition, then, h is differentiable, and, oh, looky here, its derivative is equal to 0. And not only is its derivative equal to 0, that's true for all x that live in a non-degenerate interval. So it's got to be that h is constant. I don't know why there isn't a space there. Let's see, where is that? Oh yeah, there's just legit not a space there. Interesting. That wasn't just LaTeX being weird and cramming it in there. That was just me being an idiot. Alright, cool. Okay, well now we know h is a constant, and good thing we know that that constant must equal 0, because f of a and g of a are equal to each other. Now, note, in particular, it is 0. So it is worth noting you actually can modify this this proposition to have this be whatever you want. Just go with 0, because, you know, it works. But note, if you want it to be something else, just add the constant, and all the stuff is still true. Alright, beautiful. There we go. Therefore, f and g need to be equal, so f is the only differentiable function whose derivative is f, and it sends a to 0. There we go. We have now proven that every continuous function has an antiderivative on a non-degenerate interval. Good thing we've got some pretty interesting continuous functions we can look at. Obviously, the polynomials, not too exciting. It's pretty easy to find their antiderivatives. However, 1 over x. 1 over x squared plus 1. The square root of 1 minus x squared. All of those more exciting functions are going to have some interesting antiderivatives. And of course, for you stat nerds, the integral of e to the negative x squared, of course, is, you know, kind of important, I guess. I know there's like a sigma that I'm missing there, but who cares? Alright, so actually, I lied to you. That wasn't the last theorem. We'll finish off with one last fact. So let's actually prove u substitution. For homework, you're going to prove integration by parts. So enjoy that. But let's prove u sub. Alright, so formally stated, what does u sub look like? Alright, well, we've got 4 real numbers, a, b, c, and d, a less than b, c less than d. We have a function, u, that sends the interval ab to the interval cd. Now, no, not necessarily surjective, but we just know that the range of this is contained in that non-degenerate interval, and we know that it's continuous and differentiable. We know it's continuously differentiable, excuse me, so we know that not only does u have a derivative, but its derivative is in fact a continuous function, which we need to use. Alright, and then take f to be any continuous function, then f composed with u times u prime must be Riemann integrable, and furthermore, its Riemann integral is as follows. There we go. So, in other words, if you were faced with a Riemann integral that looks like this, you don't need to do that, you need to do this Riemann integral instead. Now note, u of a and u of b, doesn't matter what they are, they in fact could be equal. U of b could be smaller than u of a. Doesn't matter, it's properly and formally set up and defined. Cool. You ever had one of those? You ever have a professor get you at a u sub and then the u sub gives you 0? Sort of jerk? Yeah. Alright, cool. Okay, beautiful. So, note, again, very similar to kind of how we did u sub before, right? Whether or not you were fully aware of it, you were kind of using this stuff. Alright, well, let's prove it. So, the first thing to note is that our hypotheses, so u is differentiable, which means that it's continuous. We assume that u is continuously differentiable, so u prime is continuous. And we've assumed f is continuous, so this composition is continuous, the product of continuous functions remains continuous. So, there we go. This must be Riemann integrable. Alright. Now, how do we get from here to there? Well, let's define the function on the non-degenerate interval from c to d as follows. Note that since f is continuous everywhere, this is differentiable everywhere, and its derivative is equal to f of y, and that's good for all y that live in C to D. Right? Note, right, we started wherever the hell we wanted. Well, in this case, we started at U of A. We were clever about where we started. Now, that means that f circ u is differentiable, since u is differentiable, so by the chain rule, the derivative of this must equal that, but the derivative... why did I turn to a G? It's supposed to be a U. But the derivative of capital F is lowercase f, and so we get f of u of x times u prime. So what do we know now? So now, appealing to the fundamental theorem of calculus, we know what the antiderivative of this thing is. It's this. So if I want to compute this integral, I just plug in b and I plug in a. Right, since I found what the antiderivative of this was, it's this function right here. All right, we'll plug it in, and hey, that's equal to 0. Boom. There you go. And life's good. U sub is still U sub, and there you go. Now you've actually seen a hardcore proof of U sub, right? Probably when you were taught U sub, it was just like, yeah, this works. Probably didn't even bother proving it. Maybe they did. I don't know. I don't even think I prove it. I think all I do is say, oh, we're going to undo the chain rule, and then kind of just leave it at that. Obviously, of course, we need to be a little more careful with our hypotheses in this course. All right, there we go. So, like I noted, for homework, you're going to prove integration by parts still works the way you think it should, which is a good thing. And now we are dangerously close to the end. We got a week left, and what we're going to do is see how we can use integrals to create some of our favorite functions. Particularly, we will use integrals to create the natural log, which we will then use to create e to the x. And then we're going to go off book one last time, as is tradition, and talk about how you can use integrals to create arc sine. Or arc cosine, I forget which one. Inverse trig, that's what we'll do. Which I've kind of already spoiled how we're going to do it, but you'll see when we get there. It'll be good stuff. Alright, I'm out. See you next time.